Okay, I think we can begin. It's 4 o'clock. So welcome back everyone to another lecture of COP 3402. Today we're going to be going over process creation using the fork and exec syscalls. So I kind of revamped the slides for this lecture yesterday, so it should be pretty, I think, cohesive. Before we begin, do we have any questions from the previous lecture? Okay, so reminder, the Hello project is due today. I had accidentally uploaded the grades earlier today, and then I quickly hid them. So if you hadn't done it yet and you saw a 0 in the gradebook, that was an accident. You can check again tomorrow and you'll have the correct grade in. Okay, so we can start with homework 8. So number 1, what is a process? This should be hopefully very easy. Yeah, running program and execution, any of those answers is fine. What is standard I/O? So what are the 3 file descriptors that comprise or constitute standard I/O? Yeah, exactly. In, out, error, in that order. 0 is in, 1 is out, 2 is error. Why is it useful to separate standard I/O from our programs? Piping, but why is piping useful? Why is it useful to be able to pipe inputs and outputs from different programs like that? Yeah?
We can get complex behavior by combining simple programs with piping.
Yes, that is one definite benefit. What's another benefit of having the output of our programs separate from the program's definitions, the program's code?
When you don't have a hard-coded input or output, the program can then take different kinds of input or from different sources, and then same with the output.
Yeah.
Because it doesn't know if it's necessarily right to the terminal or to the file. So.
Yeah, exactly, and it shouldn't have to care about that. So you as a programmer have greater flexibility. You don't have to add support for all these different inputs and outputs to your C programs or Python programs or whatever that you're writing. You can instead just manipulate the I/O of that program at the command line. So third question, how would you save the output of running the ls command to a file named results.txt? A redirect, right? That's the exactly correct word. So what would if I were to try and type this, what would I type? ls, and then what's the character we use for redirect? Greater than, and then results.txt, I believe. And if we cat that out, we can see it actually has the contents of this directory that I'm in that I'm going to show you today for this lecture. Okay, any questions on homework 8? All right, so we can go on to homework 9. How can I send the output of the find command to the input of grep, grepping for the literal character period and then h, without having to create a file explicitly? Write an example dash command that illustrates this. Yep.
So you can use the pipe operator.
Yeah, exactly. So I would say something like pipe. Let's say I want to go through my user include directory like we had seen in the previous lecture. The pipe here in the middle, and then grep, and we'll say .h. And that shows us all the files that have .h in the name. With grep, if you forget to add that backslash, the dot counts as anything. So you can see we have matches here with th as well. This comes from regular expressions. So I don't know, how many of you are familiar with regular expressions? Okay. Yeah, we don't go over them in this course, but they're another generally useful thing to know as a programmer because you can use them in a lot of different languages to quickly find patterns in text. So this dot character is an instance of a regular expression being used because the dot stands for anything. Okay. How can I run a program as a background process in Bash? Note that there is more than one way. So if I were to run find and then slash, how can I pause this and then run it in the background? Control Z, and then how do I run it in the background? BG. And now that it's in the background, what I'm going to have to do to stop this process? I'll have to kill it, yeah. And I can use pkill to quickly kill a process based off its name. and that will work. Or I could do PS and find the PID and then pass that to kill explicitly. What's the other way to run that program in the background? We went over this briefly.
Just include the ampersand symbol at the end.
Yes, appended the ampersand character to the end. So if I say find user or find slash and then append ampersand here, that will run in the background immediately. And I can press Control C, Control Z, none of that works. So now I'm going to have to do pkill again. What's the difference between pkill or kill? Kill has the same arguments as pkill. Like this and like this. What's the difference if I add the -9?
The -9 will override any process, I believe, if I remember right. You said that if you don't include the -9, it's like a signal, and the process will have to wait for that signal to then be able to show the program or terminate it.
Yeah, close to that, yeah. So there's all these different signals. How can we view the signals? Does anyone remember how we can view all the different signals?
It was a man page, I don't remember.
It was a man page. You remember what section? 7, right? What is manual page 7 for? For miscellaneous. So I recommend at least knowing what these numbers represent. So man 7 signal. You can see there are all these different processes here. And the reason we use -9 is because that's the sig-kill signal. And they cannot be caught, blocked, or ignored. So there's syscalls we can use, which we won't be reviewing in this class because we're going to be focusing on using pipes for inter-process communication, not signals. But there are signals you can, or syscalls you can use, library calls I should say actually, that let you define signal handlers in your C code that will respond to certain signals being sent to your C program. That means that the kill signal may not immediately kill the program because kill by default sends the sig-term signal, terminate signal, which does not immediately kill the program. It just tells the program that it needs to stop, and the program can set up a handler to perform some sort of cleanup actions before it finishes. Okay, any other questions about background processes, foreground processes?
This might be too general, so I apologize if it is, but is the distinction between this, this is how things work in Linux and this is how things work in all of software particularly valuable in this, like looking at this stuff specifically?
So this is all based on the book. So one of the books for the course is the Linux programming interface. So what we're going over is Linux-specific commands. These aren't necessarily universal truths about how software has to work, but billions of devices around the world are using Linux, so it kind of is almost an objective truth at this point about how software works, just because that's how it's all implemented. A lot of it. But I will say that a lot of the syscalls we're using are specific to Unix and Linux machines. So you'll notice that, like for man fork, for instance, which we'll be going over today, it's in the unistud.h header. This is specific to Unix libraries, Unix systems. So a lot of these syscalls will not translate directly to Windows systems, for instance. I don't know, does that answer your question? Okay. That's not to say these aren't useful, because a lot of machines, especially servers that you'll be logging into if you're a sysadmin, they use Linux, they are Unix machines. So these commands are definitely still useful to know.
Yeah. None of these have much to do with how software runs, just how it's, how we're going to interact with designing it.
Yeah, it's Linux kernel. So what syscalls is the kernel exposed for us to use and interact with the hardware? Okay. So number 3, how can I pause Vim, put it into the foreground and then into the background? I can say A, B, C, hello, world. How can I pause Vim?
Control Z.
Control Z, and then how can I resume it? FG, foreground. There we go. Okay, any questions? All right, so let's begin with today's lecture, and I have actually some notes here on my phone that I'm going to have just on hand. All right, so today we're going to be looking at process creation with the fork and exec syscalls, and we're going to be going over, by looking at these syscalls, the way that processes are generally created on Unix systems. This was originally a one-day lecture, so we might get out a little early today. So the general flow of Unix process creation is sort of like cell mitosis, as we had talked about in the last lecture. The idea is that each process first creates a copy of itself by invoking the fork system call, and then, after creating a copy, it invokes the exec syscall, of which there are many different variants, to replace the child process's running program with a different program. So that's the general overview of what we're going to be exploring for this whole lecture. Just wanted to give you the big idea up front. So I guess, again, one question that I asked in the previous lecture, if all processes are created through duplication, where does the original process come from? System D, which is what kind of program? I mean, what's like the name the other name for system D, that if you open the man pages for system D, that also pops up? Init, yeah, exactly. So that's the init program. Now, one important thing that I want to make clear here is that child processes are initially complete duplicates of their parents. So I think I have a diagram here from the textbook that I can use to show this. The general flow, therefore, of using these two system calls looks sort of like this, where a program will be running, so we have program A here executing. It will call fork and create a copy of itself. And you can see that it's a copy because the circle here also has the letter A in it, so both circles have the letter A to signify that they're copies of each other. The child process continues running from exactly where the parent left off because it's an exact copy of the parent. And then there's some more syscalls that happen later on. We'll review those later in this lecture, but the big idea is with the exec syscall, the child can become some other kind of process at that point while it's running. And we're going to see tons of examples of that later in this lecture, but the big idea is just fork and then exec. And we won't be looking at the wait syscall in this lecture, but in your future projects, you will be using the wait syscall to make sure the parent correctly waits on the children to finish executing before it continues doing its own thing. Yeah, and one other point that I want to mention is that, which we're not going to see yet in this lecture, but forked processes, child processes, also get copies of their parents' open file descriptors. So remember how we could open files using, the open syscall? What was the return of the open syscall? What was the return value?
Integer.
What? An integer, right? Integer file descriptor. And what does that file descriptor refer to?
Whether it was successful.
So it contains whether it's successful, yeah. Maybe I should rephrase the question. Is the file's path the same thing as the file? No, right? There's an inode. There's something internal to the kernel that stores what each file has. So when we open a file with a file descriptor, we get a descriptor that's referring to a description inside the kernel. This is within the file entry table. And what this diagram serves to illustrate is that if we have one program running, one process, with two descriptors, x and y, and they're pointing to these specific entries in the file table. I'll zoom in here so you can see this better. So one single process, x and y, pointing to these entries in the table. If we call fork, then we'll now have two processes that both have the same descriptors pointing to the same entries in the table. So this will be important when we're doing the shell project later on. Won't be going over this too much in this lecture, but I want to bring it up now because this is relevant to fork creating a child that is a copy of the parent, including open file descriptors. That's a very important thing to remember. So if we close at one of those file descriptors, what syscall do we use to close a file descriptor? Close, right? If we close, say we close y in the parent process and close x in the child process, there are still open descriptors for those entries in this table. So that's something that will come up again later and will be very important when writing your project. But I want to bring it up now because it's related to, yeah.
When you say file descriptor, what do you actually mean by that? Is that like a
Literally the integer. The integer ID is a file descriptor. So the return value of open, man to open, and returns an int. And it says right here, the return value of open is a file descriptor, a small non-negative integer that is an index to an entry in the processes table of open file descriptors. So a file descriptor is literally just an integer ID for an open file in this table. Okay. So I hope that kind of cleared that up. Okay. All right, any other questions about fork, how it copies from the parent? So one other thing I'll mention that's not really necessary to know, but it's kind of cool to know for security implications, is that this process of the child becoming a copy of the parent, that's actually kind of expensive to copy everything in the parent's memory space. So what the kernel has is something called COW, copy on write, and it will actually not copy from the parent with the child until the child actually makes any modification to something in the parent's memory space. So what this means is that the child effectively is just reading from the same data that the parent has until any kind of write occurs in the child's memory, and then the kernel will actually create a copy for the child to manipulate its own memory and not interfere with that of the parent. Not really necessary for this course, kind of more of a security concept, but there have been security vulnerabilities related to this technique of copy on write. All right, so any questions about fork, exec? Maybe not exec, we haven't gone over that yet, but. So, again, it's really like cell mitosis. Like that's why we use this diagram. It's very much like that. All right, so now I think we've talked enough about the general concept of what we're going to be doing today. I want to spend the rest of the lecture going over a ton of examples. I have a lot of examples prepared. So we can actually see how fork and exec work and then combine the two acts and see how they work together. Okay, so the first one I want to look at, I have all this, by the way, all this is going to be on the website. I've already uploaded all these examples. They're all on the webpage. So if you want to go and see all these examples that I'll be going over today, they'll all be on the webpage for process creation, which you can see right here. This has everything, including my speaker notes on it. So you can view all that here. Okay, so we're going to look at first this example, fork 1. I'll open the code here in my terminal now. So what this program does is call the fork system call. It invokes it. That's the verb you're supposed to use when you're calling a system call, invoke. It invokes the fork system call, and it stores a result in this PID variable. So let's look at the man pages for fork. We can do that in Vim by just pressing capital K on fork. And it tells us that fork is in the Unix standard IO, Unix standard, unistud.h header. It has no arguments and returns a PIDT variable or value. And it tells us basically the same thing that meshes with what we've seen already. Fork creates a new process by duplicating the calling process. The new process is referred to as the child process. And the calling process is referred to as the parent process. So the return value of fork, we don't need to look at that now, actually. For now, let's just look at how fork works by duplicating the parent. So let's try running fork, running this command here. Open a separate window. Oops. What I'll do is actually set my prompt variable to be smaller so it's not as intrusive. There we go. Okay. So we'll run make. I have a make file in this directory that will compile all the examples for us. And now we'll try running this fork1 program. And what do you think will happen when I run this program, based off what we talked about what fork does? So hello world will be printed, but how many times? Twice. Now, why do we think it's twice? Yes. So if we run this, you'll see it actually does print it twice. And the reason why is because the child is an exact copy of the parent. From the point at which fork is called, there are two versions of the program running the exact same way. Just like the diagram that we saw earlier showed right here, this is really what is going on. Fork, you have two processes, but they're both still the exact same, running in, not in parallel, but both running. Okay, so let's go to the next example. So any questions so far? Yeah.
For fork, does it wait for the parent process to finish computing fork, computing the child process?
Not necessarily. So that's up to your operating system to decide. That's up to the scheduling system of your operating system. It'll choose what runs first, what has greater priority. And you can actually affect this. There's a command you can run. I don't know why it's called this, but it's called nice. You can change the program's niceness value to change whether or not it gets priority when being scheduled. But there is a way to make the parent wait for the child to finish running, and that's using the wait syscall, which we're not going to be looking at in this lecture, but in the future lectures we will, and in your projects, well, in one of your projects, you will be using the wait syscall. So. There's also a personality too. It has some really funny names for things on Unix. This is for specifying, I think, what this is like closer to the hardware. I think affects which core a process runs on. I don't know. They picked like funny names for some of these things. So, all right. So, are we going to move on to the second example? Okay. So let's look at fork 2. Let me look at my notes. Make sure I'm not missing anything. Okay. So, I guess one question is, do we think the child will have the same PID as the parent? So the same process ID? So no, it may be a copy of the parent, but it still is its own process. And to sort of illustrate this, in this example, what we'll do is actually, we're going to call sleep first. So does anyone remember what the sleep library call does? We had seen it previously. I think it's a library call. Yeah, it's a library call in manual page section 3. Manual section 3. So does anyone remember what sleep does? Yeah?
Or wait, basically.
Yeah, essentially the process waits for the specified number of seconds. So we're going to wait for 4 seconds, then we're going to call fork, and then we're going to print hello world like before, and then wait for 4 more seconds. And the reason that this program is going to do this is because it gives us a chance to run the ps command and check the process IDs of all running processes, so we can see if the PIDs are different between the parent and the child. So I'll try running this. I'll create another window actually. Maybe I shouldn't. I'll just quit this for now. Make, and we'll run fork 2. I'll have PS ready here. Fork 2, PS. Actually, I probably should do PS and then A. Yeah, there we go. So let me do that again. Okay, so fork 2 is running, has this PID. So the second process should be created now, so we'll run PSA again. And we can see there's 2 processes with the same name, fork 2, so they're both, you can see the child is a fork of the parent. The parent, this must be the parent because it was the first one that was opened, has PID 220378, but the child has PID 220382. So it's clearly a different PID. The child does not have the same PID as the parent. So I guess another question we might have is, how can we tell the child process apart from the parent in our C code?
Just compare the PIDs and take the smaller value as the parent?
Yes, so that's close. I haven't revealed to you yet how the fork process or syscall actually works, what its return value means. But yes, that's pretty much it. We would just check the PID of the result. So let's look at the next example, fork3.c, to illustrate this. So actually what I'm going to do is make this a little bit taller. Here we go. Okay. So in this example, we're calling fork. And now we're saving the result in this PID variable, and I'm going to actually show you now what this PID t value is. I can open the man pages for this as well. It is assigned integer type as a type for storing process IDs, process group IDs, and session IDs. It is assigned integer type. So we can print it using, we should be able to print it using the %d specifier, format specifier. And here, in this code here, we're actually checking, yeah.
How inaccurate would it be then to think of the ID underscore t's that we were just looking at as children of the integer class?
It's not quite accurate because they don't always, I mean, maybe you could think of it that way. Yeah, it just depends on how they're defined. They might be defined as, it really depends on how they're defined in the kernel. Yeah. Okay, so where we were. So I want to show in this example how we can actually use the return value of fork to distinguish between the parent and the child and an error. So when fork returns, it returns this PID value. In the case of an error, this PID will be -1, so we can check this here. And then use p_error and then exit like we saw before. When it's 0, that means we're in the child process. So the child is always 0. That's something to really take note of. Fork always returns 0 in the child process. And then in the parent process, fork returns a non-negative, a positive integer that is going to be the ID of the child process. So fork returns 0 in the child, and then a positive integer in the parent. That is the PID of the child that was created. Okay, so any questions so far? Yeah.
But if you have like a double fork, so like a child forks,
Mm-hmm.
wouldn't the PID for both be 0?
It depends where you fork. So if you're calling fork inside of this child here, if I call the fork again, then since we're already in the child, we would have to check for 0 here as well to see whether or not we're in the child of the child. But that's kind of confusing. What you typically see happen when people are using the fork syscall with multiple children is that the parent is sort of like the one orchestrating all the children, and the parent forks each child off of it. So it's iterative, not nested usually. At least in this course, we'll only be using that approach. This prevents confusion with having like hierarchies of forked children. So, yeah. Okay, so let's try running this. Or else, actually I can just run make. Fork 3, we can try running this now. What do we think the output will be? Assuming there's no error.
As on when they each get scheduled.
Yeah, so we'll see these two lines, but we don't know what order they'll appear in. Let's try running this. You can see it actually tells us the parent ran first with the PID of the child listed here. And then we see the message printf from the child, which came from right here. One more thing I want to point out is that you might notice that we're calling underscore exit in the child. So if we open the man pages for underscore exit, we can see it's in the unistud.h header. And it tells us here, exit terminates the child process immediately, or the calling process immediately. It does not close open file descriptors. Well, open file descriptors are closed, but they're not flushed. The reason why you would want to use exit in the child and not in the parent is because just how you can set up signal handlers in the parent to handle signals coming from other processes, a process can also set up functions to run on exit. You can set up exit handlers. There's syscalls you can use for that, or library calls like @exit and onExit to do this. And the normal exit library call here would trigger those onExit functions. But we don't necessarily want the child to trigger those because those exit functions might do things like close open file descriptors or free memory, which we may not want the child to also perform as well. So typically it's good practice inside the child to use underscore exit, not regular exit, to avoid accidentally triggering any exit handlers twice. Yeah?
Is this method of statement in the
So very close. I'm glad you asked that because the very next example we'll see the common idiom for using switch fork, which is switch fork. I just kind of gave it away. But typically you don't use if else. You use this structure here. This is like the switch fork idiom. You'll see this a lot in the textbook if you're reading it, and in the code you're writing, you might want to use this because it's, I don't know, it looks pretty clean to me using this kind of structure here. So the idea is we just set up different cases for each kind of result that fork could return. And we're assigning to PID inside the switch label directly, so we can access the PID value later. Okay, so any questions? This should behave the same as the previous command. Yeah, different PID, but the same kind of output. Okay, so are we all somewhat confident with fork, how it works? You'll have to be using it in one of your projects coming up, the shell project, which I'll be explaining later. But yeah, I'd recommend brushing up on fork. It's one of the core syscalls for this course. Okay, so these are all the same examples I went over. Yeah, okay. So next we'll go over exec, but before that I think we can take attendance now. So I'm going to stop recording. Okay, so let's resume going over the next of the two syscalls to review today, exec. So exec is not a single syscall, but rather a family of syscalls, as we shall soon see. So one key thing that exec does, well the only thing that it really does, is it replaces a running process, a running program, with a different program's instructions. So to be clear, exec does not create a new process. That's what fork does. Exec only replaces a already running process with a different one. So is anyone taking computer architecture, or computer organization, I should say? Computer logic organization? Yeah. So how do we think maybe exec works? Like, what do you think was going on at the hardware level with exec? What's the variable that stores the next instruction to be executed? The PC, right? The program counter. So how do we think exec is working under the hood? It's just setting the PC to a different instruction, basically. So it copies some memory over as well. It loads the new program's memory or instructions into memory, and then it just sets the PC to that instruction and starts from there. That's I mean, not exactly what's going on, but generally, or I guess broadly speaking, that is what exec does. Yeah, so just to make it very clear, to drive the point home, that exec does not create a different process. We're going to be using exec with this program here that I wrote called getPID, or yeah, just getPID, which all it does is just invoke the getPID syscall, which is only useful in this one lecture for this one example, to get the PID of the currently running process. So I'll show you this here. Yeah. getPID.c, just simply, if we open the man pages for it, just gets the current process's ID, it returns a PID type, as we would expect. So this program, getPID, will just print the PID of the process that when it's compiled. So we can try running this, make getPID, and then run it, and it just prints the PID of the process. Now what we're going to do is open this next file, exec1, to show how exec works, and also just show that exec does not change the process's ID. So let's take a look at exec1.c. And let me actually delete this comment. What we're first doing is assigning a string the path of the program we want to run to this path name variable. So is this a relative path or an absolute path? It's a relative path, right? Because it starts with a dot. Then we're creating this argv variable to store the arguments of the new program we want to replace the current process with. And this argv list needs to be terminated with a null. That's a requirement that exec has when you're using exec_v specifically. So I'm going to open up the man pages for exec here. And you can see there are all these different kinds of exec functions or exec syscalls. They all start with exec, but they have different suffixes at the end. Maybe suffices, I don't really know the plural of suffix. The one we're using now is exec_v. So the v stands for variable, so you pass a variable in for the arguments. So we're passing in, as the first argument, the name of the program we want to run, and the second argument is going to be the arguments for that program. And by convention, on Unix machines, at least, when you run a process, its first argument is implicitly set to the name of that process as it was run, the name of the program as it was run from the command line. So that's why in this first argument here, we're setting the name again. And all the exec functions we're going to see today operate in sort of like this, similar to this way, where the first argument is going to be the name of the function we want to run, the name of the command we want to run, I should say. And the subsequent arguments are going to be the arguments to that program or some other kind of things you want to change about how the program executes. Okay. So that being said, what do we think is going to happen if I run this code here? Yeah, so let's test this out, and we can see the PID is 221930. Okay, let me see.
Not have a return value?
So that's a good question. Yeah, that was actually my next question I wanted to ask you all. Why are we throwing an error immediately after the call to exec? Why would it be an error for the execution to continue?
Because exec should like overwrite the code you're originally running or the code you called. So you can still run to it after the exec call, it didn't work properly.
Exactly. So exec, when it runs correctly, should replace the current process with a different program. So if the current process is still running, that means something went wrong. So we don't even have to check for errors with exec. You can just immediately throw an error because if you're still executing your own code, something went wrong. So what I want to do here, just to illustrate one more point, is call the sleep syscall, or library call, I should say, and check the process ID of this process before and after the call to sleep, so we can make sure that it's the exact same PID. So let's run exec1 down here. Oops, ps-a. You can see its PID before the call to exec is 222015, and after the call to exec, it's still 222015. So you can see the PID is preserved. Okay, so next question, what if I wanted to run a program that was not on my path? So in this one, or I guess, yeah, a program not on my path. Like a program in my, one of the ones we've been using in the command line often, like ls or cat or find. How would I run that program? A program that is on my path, I should say. So the way we run a program here is with the relative path, /get PID, because it's in my current working directory. How would I run a program like ls or find or cat? Yes, I would use the absolute path to that program. So if I go to my next example here, you can see for calling ls, we actually specify the full path to ls. You can see it actually prints all the contents, contents in my current directory. This is kind of annoying because we should be able to take advantage of that path variable that I mentioned earlier. Can anyone remind me what the path variable is? The path environment variable? You've seen it a few times. Yeah.
The path is where you store a program that you want to execute without putting the full path.
Yes. So I can print the contents of my path variable. I can actually use this shell command here, printenv, which will print a variable you pass to it. So I'll pass path to this variable. And we can see I have this whole program here, this whole big list of directories here. I'll pipe the output to grep to search for my user bin directory. See, it's right there. So your path stores a list of directories separated by colons. And when you run a program without any path prefix, so I just type in ls or cat, your program, your shell will actually look in each of these directories one at a time, and it will look in those directories for a program matching the name of the one that you typed. And if it finds one, if it finds a match, then it stops looking and just runs that program. So I can type in which ls to see that which is in the user bin directory, user bin ls. So that's probably where path stops, where the shell stops when it's looking to run ls. It probably just stops after checking user bin because it finds ls there. So the reason why we can't use, but if we try to use the path in, let's see here, this example here, it's not going to work. If we just call ls as is, I don't believe this will work. Yeah. No such file or directory. Because we're not specifying the full path, and this call to exec does not have access to our full path. So it doesn't know where to find that, where to look for that command ls. So any questions about that? Yeah.
So you're using path to find like the absolute yeah, so actual ls that we can use the syscall.
So when we run a command in the command line, ls, for instance, it just works, even though we're not specifying the full path. We could also say user bin ls, and that would work too. But we don't have to type in the full path. We can just type ls, because ls is in the user bin directory, and the user bin directory is on our path. So the shell looks in each of these directories, and if it finds that the program we're trying to execute is in one of those directories, it will just run it and then stop looking.
So for exec, you don't have to specify if it's in the directory that you're removing.
You do. So with this variant of exec v, you do, because you can see here down at the bottom, when I try to run this, it doesn't work. Because we're not specifying the full path, and exec does not have access to the path by default.
Going back a little bit, when you were doing Keynes, look at the processes to make sure exec was running. Why did you want to see both were the same? Because if it was child, wouldn't you want a different PID?
But it's not a child. That's an important distinction. Exec does not create a child. Exec only replaces the current process. That's something that I really want to make very clear. Exec does not create a new process. Exec just replaces the current process with a different command, a different program's instructions. But exec does not create a new process. It replaces a currently running process.
And so
Only for creates a new process. Yeah.
none of the lines below will run at all.
They shouldn't. If exec succeeds, they should not.
Oh.
Yep. So I'm glad that you're all asking these questions, because that's something we should make very clear. Yeah.
So what is the purpose of using exec?
We'll get to that shortly. It has to relate with fork. We will see that very shortly, but that's why I'm showing you these two things to kind of get to the result of why we use them together. So we'll see. Yeah.
So when you do to the command or where
Yes.
you want it to? Okay.
That's the full path to the command. That's where ls is. So remember, we can use the which command to check where a program lives, where it is. So which ls. So we could also do which dash a to see all the places where it is. This is a symbolic link bin, so it's the same thing. User bin ls. So that's where it is.
Okay.
Yep. So that's all to say, this is kind of annoying though, that we have to specify a full path every time we want to run one of these programs that are already on our path. You shouldn't have to specify the full absolute path to them. It's kind of annoying in our C code that we have to do this. I would like to be able to just write ls here and ls there and be done. So that's where the next variant of exec comes into play. Exec vp. So we have a new suffix at the end of exec. So what do we think the p stands for? Path. So now I don't have to specify the path to ls. I can just run ls. And I'll delete this for now. So if I run make and then run exec3 here, you can see it actually successfully runs runs exec in the current directory. Maybe I should make this a little bit smaller. Yeah. All right, any questions on that? Yeah.
What's the difference between exec VP and exec V? Like,
So exec VP is that the P means path. Exec VP has access to the path variable. It will inherit the same path variable as the original process had. So exec V does not have access to the path. Yeah.
So when you're using exec VP and you run the ls command, is it just showing the contents of where you are currently running that command at?
Yes. Yes. The current working directory. Yeah. Mm-hmm. So one more thing, just to illustrate here, is that we can actually pass flags to programs via exec by passing them as subsequent elements of the argv list here. So the first argument should always be the name of the program to run, but the subsequent elements can be arguments to ls. And then the last argument should always be null. So ls-1 prints every element on its own line. It's one element per line. That's what the 1 means. So if I were to run exec3 here now we get the output of 1 element per line. 1 entry per line. Do you have a question? No, yeah.
Would you say it's generally safe to use exec VP, or like we're just writing out the whole thing?
If security is your primary concern, you probably want to use the full absolute path. But I would argue that if you're concerned that somebody has compromised your path variable, you might have other things to worry about. So, yeah. Yeah.
Why would you use exec V over exec VP?
Exec V over exec VP?
Yeah.
So if you want to be, okay, so I could, in theory, someone on your system could log in and then write an alias or something that changes ls to instead be a different command. So I could say, or they could like add a file to the user bin directory that replaces ls with like a backdoor that lets somebody log into your machine when you're not aware of it. So then in this case, running ls here, we just look in the user bin directory and run whatever it finds first in the path. I mean, yeah, I don't really have an example on hand to show you, but you could, since this is just looking in the directory for the first instance of an ls program, an attacker could maybe modify your path to hide the different ls program there that is like malicious. Yeah, that's the concern. Yeah.
Or wouldn't you just use execvp all the time?
I mean, I probably use it most of the time, but I don't know if everybody uses it or not. I mean,
Why
where
would you use the other ones if like execvp can do everything?
because exec v, one example like we just talked about, it might be more secure to specify the full path to a program to run, so you know exactly which one you're running. You're not relying on the shell to look up the correct program in your path, which may be one that's been compromised. That's one reason. Also, another reason is because, actually no, that's the only reason I can think of right now. Yeah.
Would it be more efficient to run V instead of VP because you don't have to search the back?
Might be a little bit faster. Yeah. Yeah.
I can think of maybe have the same program name on two different paths.
Yeah, that's a good example. Exactly. Yeah, you have the same program in two different directories that are both in your path. So I got my path here. Maybe in like this long directory and this bin directory here, I have another program called ls, and in here I have another program called ls, and here I have another program called ls, and I want to specify which exact ls version I want to run. I have to specify the full path to do that. So that's another reason why maybe you'd want to specify the whole path. I don't know, does that hopefully answer your question or give some? Yeah, okay. Yeah.
For exec VP, could you still pass the full path if you wanted to? Like if you were running something that wasn't on the
You can, yeah, you can. Because it gives the program the path, but the path is only used when there's no absolute path already given. So we can try running this, and I think it should just work. Yeah. Okay, so let's go on to the next example. See if there's any, okay. Actually, but before that, quick quiz. So this kind of relates to somebody's question about why we even use exec, what's exec useful for. So remember the previous diagram, cell mitosis, process mitosis. How can we change a child process to run a different program if the child is always initially a complete copy of the parent?
You could do the switch statement and then do exec if the PID is 0.
Yes, exactly. So is that what everyone else is going to say? Yeah. So switch fork and then exec in the child. And this is how process creation usually goes on Unix systems. Switch fork exec, switch fork exec. So I think one student asked earlier if there's like, if we go with nested hierarchies of like processes. That is actually pretty common, but for us in this course, we're not going to be doing that. We're going to be doing a different way of creating processes, more like a flat structure. Yeah.
If you set up code to infinitely make a child process and exec it just over and over again, would that eventually crash?
So I have a funny story. My brother was a high-ranking member in a fraternity when he was at UCF. And I once went to Fort Lauderdale Beach with him and some of his fraternity brothers. And I had a nice conversation with, well, we were at a pool hanging out at an Airbnb, with a guy in the fraternity who had the source code for this thing on his arm. This is a fork bomb. A fork bomb does exactly what you just described. So it's a very concise and dangerous piece of code.
Has there been like any updates to like prevent that from happening, or
Just don't run a fork bomb.
is it as a no?
I mean, you can have, all right, so there are ways to maybe prevent this.
Like if I'm gonna have to use this right now and try that, would it go wreck?
So there are limits set for different users. So right here, max user processes. So mine is set to this number. On users, it's probably a lot smaller. So you can't just keep forking and execing. Yeah.
In Windows, it'll offload non-essential processes, so it'll just get cut before the whole OS actually crashes. Likely, because they'll say, "Oh, this process is non-essential. We have to preserve the OS."
We'll have a million.
Maybe.
Shut it down.
I don't know. This is Linux, so I don't really use Linux. So yeah. But yeah, what this snippet is doing is what you just described, fork and exec. But it's doing it via shell commands. I think right here, yeah. But they don't even have exec, they're just forking. While true fork. So yeah.
But wouldn't that not be a problem because it's only after a child process differentiates it, makes itself different than the original, that it actually allocates different memory to it. That's like just point to the same thing?
The memory is the same. Okay, the storage, the memory on disk is the same, but the process still needs to have its own. There's still it's still its own process, like on RAM. Like the process is still running, but the storage memory that's stored like on disk is still going to be the same. Shared between them. Well, I guess the instruction memory that the program counter is pointing to would be the same. It still would be in RAM. So yeah.
COW doesn't save you any RAM?
See what?
COW?
COW? Oh, copy on write. So, okay, I don't want to get too deep into the weeds here, and also I'm not
Sorry.
like an OS guy, so I'm not like super familiar in all this. But basically, programs have both instruction memory and they also have data memory, which stores the values like open file descriptors, for instance, and values of variables. Each program at a minimum, each process needs its own instruction counter, which is going to be different because they're all running at different points. So I don't know exactly what is copy on write or not. I don't know that like values that are stored are going to be only copied when they're modified. So like variables and whatnot will be changed. Yeah, I don't know about the deeper workings. Sorry. Yeah, I don't know. Okay, so any questions? All right, so to answer, I think it was maybe your question earlier about why we use exec. So the reason is because so we can change child processes to do different things. And I think now is a good time for me to ask this question. Yeah. Can you think of a program that does this? It crawls fork and then changes the child's behavior with exec.
It's kind of similar to Git when you branch and you open a new branch.
Well, that's a similar idea of branching, but it's not creating a different process necessarily. So there's a hint. We've been using this throughout the entire lecture. There's a program that runs all the time, and then we tell it to do something, and it forks and execs. Yeah? Getting very close, much closer. Yeah?
LS?
Very close, very close. What is LS run by? Not the kernel, but
No, terminal.
the terminal, which is the shell. Yeah, it's not the kernel, but the shell. Yeah. So the shell is a classic example of this. And actually, in the MyShell project coming up, you're going to be using this approach to implement a shell. It's actually very easy to implement your own rudimentary shell by just using fork and exec. Because, I mean, all you're essentially doing is just taking user input and then passing it to a call to exec each time. You just fork and then call exec, fork and then call exec for each command the user runs. Each of these. So, yeah.
Does the one you fork from, like the parent, does that ever go away?
So, no. The idea is with the way you'll be implementing your shells and the way that I think the bash shell does it itself, is that the parent is sort of like, if I can draw this, might help. The parent process is just sort of creating a bunch of children off of it, but it's never, the children aren't creating their own children. It's just the parent creates these children and then manages them all. Make sure they run at the same time. So something like, yeah, like this. The additional wrinkle of complexity here is how do you manage pipes? So how do you have these processes communicate with each other? Yeah.
Wait, that happens every time you run a command.
Yeah, it forks and then calls the other command, calls the next process. Yeah.
Like a while loop with fork on it?
Something like that. You're going to have to implement that yourself in the project, which will come in the future. Yeah. And some commands actually do not call fork. Can we guess which kinds of commands? Remember, there's two kinds of commands we had seen. The ones we get help with man, and the other kinds that we use to get help with help. What are those commands that we cannot get help with man with? Kind of a confusing sentence, but so
Wouldn't it be split off because it's just like calling something? So it would just go into that thing?
No. So these are ones that don't. Kind of. So let me rephrase this in a different way. So we use man for program. So what do we use help for?
I think shell built it.
Shell built-ins. So certain programs like CD and Echo are shell built-ins. So they actually don't even fork. They just run within the shell. They're built in as functions defined in the shell directly. And the reason for this is for performance. Because fork and exec are syscalls, they have a little bit of a performance overhead. So it's faster to implement those as C functions within your shell definition, your shell implementation. Yeah.
So those builds, they don't fork, so they just exec?
They don't even exec. They're built into the shell. The shell just runs them. The shell is written in C, so there's a C function somewhere that implements echo inside of bash. And there's actually ways to extend bash with your own built-ins if you want to. It's kind of cool. Okay, so hopefully that was actually a good example of when you want to use fork and exec. So any questions before we continue to showing how we can actually use fork and exec together in our own C code? Yeah.
So when we run a program like on a terminal and stuff like that, does it run the shell or does it fork and exec as well?
So if we're running a program, not a shell built-in, then the shell will fork, and then the child will exec that new program that we executed. So if I run ls, because ls is not a built-in, ls is a program, what just happened is the shell created a child, it called fork, created a child, and the child process called exec to replace itself with ls, something like what's up here. So I think maybe we should move on to the next example to really illustrate this. I think the next one is, oh, there's actually one more, exec for, before we go on to combining them. Oh yeah, this one's kind of cool. I think this is worth showing as well. All right, so remember that printenv program I showed earlier? How we can use it to print environment variables? Well, we're going to be using that in this example, and we're going to be execing it. But here we're going to be introducing a new kind of exec, or two different suffixes that are new. So we're going to be looking at exec LE. So L stands for list. It means you pass the arguments as a list directly to the exec system call. So instead of creating an argv variable for passing the arguments to the program, we're just going to pass them directly to exec. So this is equivalent to user printenv. Oops, there's a typo here, gotta fix. User bin printenv course code. You can see it prints nothing because I haven't set that variable to any value, so it's an empty variable. The E suffix lets us specify an environment for our new command to run under. So environment has a bunch of shell variables that this program can access. So the way you specify the environment is a list of values like this. We have a variable name, then an equal sign, and then some value that's assigned to. So if we run printenv course code here, we get nothing. But what do we think we'll get if we run this program? Under the environment in which course code is assigned to COP3402. Exactly. Yep. So with exec-e, we're passing this envp variable, which stores the new environment for the program to run under. And in this environment, we're assigning the value course code to COP3402. So when we run user bin printenv here, and pass it the argument course code, it will print the value COP3402. This can be useful for running commands, exec commands, under different environments which have different values that can affect how those programs run. So you might have noticed, like for Git, we had to set the, I think the editor variable. That's an example of a variable that affects how a program runs. So there's different kinds of variables like that in your shell. Okay, any questions? Oh, yeah.
I don't know if this is a dumb question, but like, why do you have the underscore forward for like when you were calling that one, as opposed to just calling it normally?
You mean here?
Yeah.
Because this is exec4.c that I'm editing right now. Yeah.
So you specified the environment to be that?
I specify the environment in this program before calling exec. I created this value for storing the new environment for the program to run. And then when this program is run with exec, this printenv program will be run under an environment in which the course code variable is assigned to COP3402.
Okay.
Yeah.
The print env, is that just a file that you have that has C code that does printf, or what is it?
It's another program on your machine. So you can see it's in my user bin directory. It's another executable program. Yeah. Just prints environment variable. You can see it's on my path. User bin print env. That's why I specified the path here like this. So I know this might seem a little confusing or maybe irrelevant showing this e suffix, but now we've seen every single suffix that there is for exec. So there's all these different kinds of combinations and ways to combine the suffixes that we've seen. So to be clear, that is L, P, LE, VP, VPE, and by showing, I think hopefully, now that we've seen examples of all these different suffixes like by themselves, you can hopefully get the idea of how all these different exec functions work. They all behave a little differently. All it is that they all have support or lack support for the different features that the different suffix denotes. So for this course, you're just allowed to choose whatever one you want. Whichever one you happen to like most, you can just use that for all the projects and exams or whatnot. Okay, so now I think we can move on to the two longer programs that I have, which will be the end of this lecture. Fork exec 1 and then fork exec 2. So these ones are a little bit longer, but they put together everything we've seen so far, and I think you should be able to read them at this point. So I'm going to actually close this window and open fork exec 2, or 1.c, I should say. All right, so it seems like a lot of code, but we'll step through it line by line, and I think it's not as bad as it looks. So first we're declaring this PID variable with the PID type that we've seen already. Then we're assigning the PID to the result of fork. We're using this switch case idiom that we saw earlier, switch fork idiom. So in case of -1, that means an error. What does 0 signify? The child process. So in the child, we're going to use this putS variable here, or library call here, which just prints a string. It's like printf. Honestly, I'll just change this to printf to avoid it being more confusing. We're going to assign the program to run to be printenv, assign its arguments to be printenv and then foo, so we're going to pass foo to printenv. And then we have this new environment here, foo equals this message is the value of foo. Then we call exec VE. So what does the V stand for? What does the V mean? Variable. And what does the E mean? Environment. So we have to specify the environment as the last argument here. And I guess one more thing to note is that these arguments, these variables, have to be lists of strings that end in null. They both have to be null terminated. That's how exec knows when it's reached the end of a list. And why are we exiting and emitting an error message here after exec? So exec should not return. When exec succeeds, the process's instructions are replaced with that of the specified command, and so exec should not return. In the parent process, we just say that the parent's still running and print the child's PID. So let's try running this. I'll set this variable here to be $. There we go. Okay, and now we'll run fork exec 1. What do we think this will print? Maybe that's too small. Yeah. Yeah.
This message is the value of food, and then the parent is still running, child food.
Yeah. Let's try running this. You can see it says this, the parent is still running, child PID, inside child process, this message is the value of foo. So inside the child process, we printed inside the child process right here. And then this message is the value of foo because that's the value of the environment variable foo, which we printed because we're using print env. Yeah.
How does that default thing work in the switch cases?
Oh, so, okay, I thought maybe, okay, so you're not, okay. So switch case works by setting up a condition, and then what are the case labels? Does anyone know what requirement the case labels have to follow? They have to be in compile time constants, integers, essentially. So that's what these other case labels are for. And what is the default case? When is that triggered?
If no other case was.
Yeah, it's a catch-all. It's when no other case is triggered. So this last case here, default, happens when neither of these above cases are triggered. And the cases are triggered based off the value of the expression inside the parentheses. So here we're switching on the value of fork, or PID, which is assigned to fork.
So why did the default trigger if the case 0 did hit?
Because it triggered in the child, but in the parent, we saw that it also was activated. The parent is still running, child PID.
Oh, so when we forked, the parent process still ran, that hit the default, but in the
Yes.
fork hit the case 0.
Yes, because remember, fork creates an exact copy of the parent at the point at which it is called. So it's called right here. At this point, both the parent and the child are going to be executing this switch statement.
What is the, oh, never mind. Oh, and the parameters you pass in main, is that important?
No, they could be void in this case. We're not using them, so it could be empty. Yeah.
The order of output isn't always the same, right? As in, like, the parent won't always go first, or will always go first?
So on my machine, it might always go first, but I'm not sure about your machine. It depends on the scheduler, how your scheduler is going to work. So I'm not sure if that's going to be consistent. I think it'll be consistent on my machine, but I don't know if it'll be the same for your machine. Okay, any questions about this? All right, let's see the last example. All right, so in this example, let's see what we're doing. So we go to we call fork like before. We handle the error case. In the child, we print inside the child process. We sleep for 5 seconds. Then we actually call sleep again. So we set the program to run to be sleep. Set its arguments to be sleeping for 10 seconds, and then call exec. And then the parent, we just print the child's PID and sleep for 10 seconds. I think we could actually run PSA here and see that fork exec is running. And now the child has been replaced with the call to sleep. And it has a different PID from the parent. It's one more than the parent. I think what we can see here, if we run this again, yeah, so they're both fork exec. And then eventually, yeah, the child sleeps. So the child is replaced with sleep, but its PID stays the same, 225339. It's 225339 here. But before, so I'll open up the program again. Before the call to sleep in the child was just a copy of the parent and had a different PID. after the call to sleep is done, the child calls its own sleep command and is now the sleep program, but it has the same PID as before. Its PID was not changed by the call to exec. It kind of puts together everything we've seen so far in this lecture. Okay, so any questions on why the output, why the PIDs are what they are, why the program does what it does? We can also see that the parent, it says child PID is 22539, and that 339, and that's supposed to be the exact same PID. So fork does return the exact PID of the child. So does calling exec change the calling process's PID? No. Does calling fork, well, when you call fork, does the child process receive a new PID? Yes. Yeah. Does exec create a new process? No. Okay. Good. Yeah. And fork creates a new process. So yeah, that's it. That's it for today. That's all the examples I wanted to go over. I think you should all have a decent understanding, good understanding of how fork and exec work, and we'll be using those heavily in the later project in this course, the MyShell project. So yeah, be sure to practice. If you have questions, you can ask me now. I'm going to end the recording.